to everyone. We are starting our descent, so please buckle up and I hope you enjoyed the flight, blah, 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 however all that goes. Okay, in Chapter 10, we're comparing more than one population at a time. Quite often, 3 or 4 or more. In 10.1, we see something called a chi-square goodness of fit test. So it introduces a new statistic for us, and the variable looks like this. It's a capital X looking creature that's kind of cursive and wavy and sexy and all, and then it's squared, and so it's always going to be a positive value. We'll look at the table for that here in a little while so you can see how different it is from normal distribution or t-distribution. But I just wanted to give us a brief overview of some other things you could study in statistics. So although Chapter 10 is very important in the statistical world, it's minimal on the final, so I'm not trying to give it to you to stress you out. I would just like for you to be exposed to other great things in statistics. So it's used to test whether a frequency distribution fits an expected distribution. And the null hypothesis states that the frequency distribution fits, and the alternative says it does not. And that's as simple as it gets. So we're just going to try one. We're going to build it by hand first, and then I'll show you how to do it with StatCrunch. So this is a multinomial experiment, and here we have the results of a survey of tax preparation methods. And you can see that there's 5 different methods that we're interested in. And the probability for each possible outcome is fixed, and we're told that the distribution is 25%, 20%, 35%, etc. On our next slide, you'll see that we want to test the previous survey's claim by using a goodness of fit test. And so we're going to say that the distribution is what you saw, or that it differs from what you saw. Now, what we don't have the power to do with this type of test is show where it differs. Okay, so we're either going to say it matches or it doesn't match. And so in order to calculate the test statistic for chi-squared, you must look at all the observed frequencies and all the expected frequencies. Expected frequencies are assuming the hypothesized distribution, and the expected value is going to be the number that was sampled times the probability for each category. So we did a survey, and this is what we ended up with. We selected 300 people, and we asked how did they do their taxes, and this is what we saw. Ta-da! Well, on our previous slide, we saw what was expected. So these are the observed. What did we expect to find? So to do the expected, we have to look at 300 times 25%, 300 times 20%, 300 times 35%, 300 times 5%, and 300 times 15%. This will get us our expected values so that we can compare them to the observed. Now, just looking at the numbers, the accountant, for example, is 71 as what we observed, and we expected 75. And 300 people, is that off by much? Not really. But if you look at by hand, we observed 40, but we expected 60, so that's a lot lower. The 101 and the 105 are similar, and so forth, okay? So the question is, are they off enough from each other for us to throw out the claim that says these are the percentages that it should be, okay? So as you flip through the sides, you'll see, okay, here's our observed, here's us calculating our expected, which is what we just did, and then you run a goodness of fit test only if the following are true. The observed frequencies must be used obtained by a random sample, which we have, and all of the expected frequencies must be greater than or equal to 5. So if we go back and look, the lowest was 15, so we meet this requirement also. Now, chi-squared is found by summing up the following. So you can see the formula right there, but chi-squared is the sum of every observed minus expected, and then you square it so that it won't be negative, and then you divide by the expected. So chi-squared test is always a right-tailed test, so it's always going to be greater than, no matter what. So now we have to come in and do this for each one of these. Well, thankfully, we have a slide that does it for us. So let's go look at our work. Oh, Jennifer May, you took the slide out. Okay, well, let's look at the actual work here. If you have the slides from the book, then you'll see this work. So give me just 1 second. Okay, so the number crunching here is a little bit tedious, but bear with me because I'm going to show you how to do it in StatCrunch in 2 seconds. So you're supposed to take the observed value minus the expected value, square it, and divide it by that expected value. And you do this for each category, so we have to do this 5 times. So the observed value minus the expected value divided by the expected values. So I don't have the expected values here on the screen, but they're on the previous slide. So the observed value minus the expected value squared divided by the expected value. We still have to do this 2 more times. So you're comparing the distance from what we expected it to be when we sum this all up and magically get about about 35. This is our chi-squared value. Chi-squared is equal to 35. Now, we need to know a little bit of something, and you don't see that on any of our slides, but the degrees of freedom have to do with the number of categories minus 1. So we have 5 categories, so our degrees of freedom is 4. Let's take a look at what the chi-squared table looks like. So this is from your textbook, and if you notice, we're not only going to do right-tailed. This is if we were going to do confidence intervals, which we skipped that in our course. So if you run across the top, this reads like a T table. So you pick up your degrees of freedom, which is 4, and then you're looking for one of these values to be as close to your chi-squared value as possible. Well, our chi-squared value is 34 or 35, so that's way over here. So the p-value then is much smaller than 0.005. Okay, let me show you how to do this in StatCrunch then. So if you want to pause the video and open up StatCrunch, I'll show you real fast how you can do it there. Okay, so in order to use StatCrunch, you need one column with your observed values and the other column with your expected values. It's a good practice to change the variables and just put that there's your observed and your expected. So I just changed them to O and E. If you come into Stat and you go to Goodness of Fit, chi-squared, then you select the column that has the observed, select the column that has the expected, and you can just click Compute. It will then give you a table that tells you your p-value is much smaller than 0.0001, and then it gives you a table with all the information. So that's much faster than all the number calculations. So in your homework, take advantage of that, dump the data into StatCrunch. You will have to create your expected value column, but that's easy enough to do. And then run a chi-squared goodness of fit test. Thanks.